forward join. Then horizontally, we made the liquid hydrogen tank, followed finally by the engine section. To properly align the flanges as they come together, we use live photogrammetry on 6 bolt locations to make sure they properly align.
Operation Icebridge. You may know it from the beautiful photos that pop up in your feed. But did you know that Icebridge is the largest polar airborne survey of its kind? Icebridge was designed to study annual changes in the thickness of sea ice, glaciers, and ice sheets, as well as bridge the data gap between the ISAT and ISAT-2 polar observing satellites. Between 2009 and 2019, Icebridge flew over 1,000 scientific missions, gathering data that has redefined our understanding of the cryosphere. So let's take a look back at some of the mission milestones from over the years. One of the first steps to measure sea ice thickness is to get a handle on the amount of snow that accumulates on top of it. The Icebridge team pioneered the use of a snow radar instrument to gather the first widespread data set of snow thickness on top of both Arctic and Antarctic sea ice. Closer to land, the point at which a glacier begins to float is called a grounding line, and it's a very challenging place to measure ice thickness. Using 2 instruments, a radar sounder and a gravimeter, the Icebridge team was able to survey hundreds of these complex transition zones, enhancing scientists' understanding of the rapid changes in glacier behavior. In 2011, NASA scientists discovered a 19-mile-long crack across the Pine Island Glacier, one of the fastest retreating glaciers in Antarctica. The crack measured 260 feet wide and 195 feet deep when it was observed. Throughout the mission, Icebridge was able to map rifts in ice shelves prior to major calving events. And while these events are part of a natural cycle, Icebridge's observations helped scientists better record the changes in calving frequency and model how they may be related to a thinning ice shelf. The motion of the Antarctic ice sheet, the largest ice sheet in the world, is heavily influenced by the topography of the bedrock underneath. In 2013, the British Antarctic Survey used over 25 million measurements collected by Icebridge and other projects to develop a 3D map of Antarctica's bedrock topography. Called BedMap2, it provided unprecedented detail of how the continent's bedrock shaped the flow of the ice sheet. Data collected by Icebridge enabled many discoveries in the Arctic as well. A team from the University of Bristol used Icebridge's radar data along with other data sets to uncover a 400-mile-long canyon buried under nearly 2 miles of ice. This hidden canyon is longer than any other known on Earth and provides a critical clue to modeling how melting ice is funneled into the Arctic Ocean. Using ice-penetrating radar data collected by Icebridge, scientists were able to build the first ever age map of the layers deep inside the Greenland ice sheet. For the first time, scientists can navigate the history of Greenland's ice layers, extending previously collected ice cores to better understand the ice sheet's history and help build models of its future. An international team of scientists used decades of NASA data to uncover a massive impact crater hiding beneath the Hiawatha Glacier in northwest Greenland. At roughly 1,000 feet deep and more than 19 miles wide, it is potentially one of the youngest large impact craters on Earth.
6, that's gonna 5, 4, 3, 2, 1. Mark on the overpass 0435, 350.
Ice was bridged on April 8, 2019, with a direct underflight of the ISAT-2 satellite over Arctic sea ice. For the first time, both ISAT-2 and Icebridge would be taking the same elevation measurements over the same ice. These mirrored measurements were critical in validating the satellite's instruments and continue the legacy of Icebridge after the mission was completed. Over the course of its 11-year mission, Icebridge completed 1,056 scientific flights and provided a wellspring of data that fueled the publication of more than 660 papers and counting. The mission provided new insight into the processes driving the changes in the cryosphere, helping scientists better understand what we can expect in the future.
Early in its history, Mars had a far more hospitable climate than the one that we see today, with a thick atmosphere and abundant flowing water. So how did it evolve from warm and wet to cold and dry? Since 2015, NASA's MAVEN mission has been investigating this question by studying the red planet's upper atmosphere. Now, it has mapped high-altitude global wind patterns at Mars for the first time. During the closest part of its orbit, MAVEN skims through the upper atmosphere, ingesting air molecules and determining their composition with an instrument called NGEMS. MAVEN can also rotate NGEMS back and forth to measure the air's velocity. These measurements provide a snapshot of wind speed and direction along a track of MAVEN's orbit. Because the orbit evolves over time, or precesses, the spacecraft's closest approach to Mars drifts across the planet, allowing it to take snapshots at different locations. Over the past 4 years, MAVEN's tracks have added up, crisscrossing Mars at many locations and at various seasons and times of day, wrapping the planet in a web of observations. The measurements reveal how the winds vary with location and evolve throughout the Martian year. Now, scientists have used MAVEN data to build a global map of wind currents roughly 200 kilometers above Mars, the first time that winds have been mapped globally and at such high altitude anywhere beyond Earth. Within the new map, scientists discovered an unexpected feature: imprints of rugged terrain far below. As an example, during 2 of its orbits, MAVEN saw winds above the Tharsis Plateau diverting away from elevated terrain, driven by giant shield volcanoes reaching twice the height of Mount Everest. Here's how the process works. Down at the Martian surface, winds are forced around and over obstacles when they encounter mountainous terrain. Disturbances in surface-level winds also disturb the air above, propagating up through the atmosphere as gravity waves. When they reach the upper atmosphere, the gravity waves block the high-altitude winds, causing them to alter course and allowing MAVEN to sense the presence of mountains and valleys on the surface while skimming the edge of space. High above Mars, MAVEN is studying the upper atmosphere and reaching out to feel the breeze. It has now made the first measurement of high-altitude global circulation patterns and discovered a surprising connection to features on the surface. These measurements also shed new light on ancient Mars with its thick atmosphere and its warm, wet climate. By revealing how the climate of Mars works today, MAVEN is helping scientists piece together the early chapters of its dramatic history.
I'm Mark Weiss, and I'm the Logistics Element Manager for NASA's Gateway program. And this is Ask NASA. We're here to answer your questions about Gateway. All right, let's get to the questions. First one we've got in the mailbag. Why can't we just land on the moon? We can. We did that already. Gateway is not about just landing on the moon. Gateway is about giving us access to the entire moon and doing it in a reusable, sustainable manner. Gateway is our command and service module that will enable us to explore the moon. It's a small spaceship, and it enables us to dock Orion, get down to the surface of the moon, and practice at a place that's really close, so we can eventually explore beyond to Mars. All right, next question. When will the first module be ready? So Gateway's first module is the power propulsion element, right now scheduled to launch by the end of calendar year 2022. That's what allows us to have all the power to start to assemble Gateway and be ready for a 2024 boots on the moon. Will the Gateway have cameras so people can watch live action? Scientists love pictures. But so do you, right? We want to share this with the American people. In this world of hashtag what's going on with Gateway, we want to share that with everybody. We will definitely be sharing what we're doing to go down to the surface of the moon and living aboard Gateway.
What's your favorite sci-fi character?
Darth Vader?
If the moon was made of cheese, could you smell it from Gateway?
No, because the smell won't travel in space.
How far is Gateway from Earth?
It's far. Gateway's in deep space. So we all can see space station fly above Earth. It's a couple hours drive equivalent above us, and when the sun reflects, those solar rays are huge. Gateway's nowhere near that size, and it's 250,000 miles away at the moon, so it's going to be much harder for us to spot it out there.
Are we taking science research to Gateway like we do with Space Station?
Absolutely. So we want to definitely take advantage of that environment out by the moon where there's less interference of what's going on here at Earth, so we can study the planets beyond.
What's your favorite part of your job?
The people. Always the people. We work with amazing people. NASA's an amazing place to work.
How many astronauts does it take to change a light bulb on Gateway?
None. They don't live up there all the time like they do on space stations, so we have to develop the right inter-vehicle robotics to make sure we can do this without them even being there. How will air and water be supplied? So water's not coming in bottles like this. That's the challenge we have to set up a commercial supply chain to deep space. We don't have a rocket launching every single day, so we have to figure this out and make sure we have everything our crew needs. Supplies, science equipment, and all the equipment they need to go down to the surface of the moon. And the air they need to breathe. Where's my eggnog? Did someone take my eggnog? It's got EVA mittens.
Do you have a question for NASA? Send your questions to our experts using hashtag AskNASA.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the Moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the Moon. Approaching the Moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the Moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the Moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the Moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the Moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the Moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our Moon and prove that together we are ready to go beyond.
All right, lift off and the clock is started.
including more than 1 ton of sample.
To go back to the spacewalks for just a minute, a fourth AMS spacewalk to conduct leak checks around the new cooling system will be scheduled later, and AMS will remain dormant until then. And during some of the tasks on these AMS spacewalks, Parmitano and Morgan made use of a special new tool developed by college undergraduates in the Houston area. Have a look at how the Artemis generation is contributing to NASA's mission right now. Each of these AMS spacewalks began the same way all other International Space Station spacewalks have, with the lengthy process of getting the astronauts into the spacesuits that support them as they float out in the vacuum of space. Want to see what that looks like? Well, here's an accelerated view of the process from this past October, when Parmitano helped Morgan and astronaut Christina Cook get ready for their spacewalk. This spaceflight is the first of astronaut Drew Morgan's career, but his 6 spacewalks to date already have him at number 27 in history in the amount of spacewalking time. Floating out that door half a dozen times is quite an achievement, but then Morgan is no stranger to making giant leaps.
I think I often describe myself as a soldier, a physician, and an astronaut. The pursuit of those happened in that order. One of the earliest memories I have is of always wanting to be in the military, of wanting to be a soldier. Quite a history of military service in our family. Both of my grandparents, my father was an Air Force officer, and I also remember my parents telling me a story about my great-uncle Clink, Harry McClintock, who was a paratrooper in World War II. He was in the 101st Airborne Division and jumped at Normandy on D-Day, and then jumped in Operation Market Garden in Holland. And that was the first time I had ever heard of the concept of a paratrooper, or what it meant to be an airborne soldier. So when I later decided and graduated from high school and I went to West Point, I knew that I was very interested in this concept of being an airborne soldier. At West Point, they had a parachute team called the Black Knights. Yeah, so I made the parachute team, and that became one of the central activities of my remaining 3.5 years at West Point. In addition to academics, after class, we jumped most days of the week, but then we were also a demonstration team, so we jumped in football games. Also, while I was a cadet, I went through military basic airborne course, which taught military static line parachuting. Specifically, the parachute aspect of it, if I go back to the time when I was a cadet, my teammates that I was selected with became my best friends in the world and continue to be to this day. And that camaraderie that we had and that dependency we had on each other, making sure that we were skilled in the aircraft, skilled in the air, our lives depended on each other to do safety checks of each other. That type of camaraderie is something that I feel now in the astronaut corps with my astronaut colleagues as well. I think about how 20 years ago I was developing those skills at an early age and didn't even know it. I'm Andrew Morgan, and I'm a soldier, a physician, and an astronaut.
International Space Station training doesn't require that astronauts jump out of perfectly good airplanes. But the course of preparation for a 6-month tour of duty on orbit lasts more than 2 years and has its own tough elements. Modern technology allows astronauts to train more safely than in the past as they prepare for the missions of today and those of the future.
Mission training for astronauts has always been rigorous. Testing our astronauts' limits, abilities, and knowledge is still an integral part of readying them for the tasks they'll carry out in space. In the Apollo era, there were so many more unknowns. Those pioneers used the best of what was available to them at that time and invented the rest. Safety was and is a top concern, but we push boundaries at NASA at great risk. Throughout NASA's history, technology has fueled the evolution of our training programs. Virtual reality allows our astronauts the benefit of safely repeating mission-specific events and activities, although some things we do don't look that different from back then. Astronauts have to be prepared for their journeys. It's the nature of all of those who explore.
Now, apart from the AMS spacewalks, the Expedition 61 crew is in the midst of a lot of cargo traffic. A Russian Progress cargo vehicle that launched early this morning should dock to the Russian station, the Russian segment of the station, on Monday morning, December 9th. And our coverage on NASA TV and NASA.gov starts at 3:45 a.m. Central Time. And a SpaceX Dragon cargo ship that launched on Thursday is due to arrive Sunday, December 8th. Our coverage begins at 3 a.m. Central on NASA TV and NASA.gov. This 19th Dragon cargo mission has a variety of cutting-edge scientific experiments on board. Here's a look at some of what's due at the door this weekend. Now, also in the area of cutting-edge science, there's a cutting-edge piece of hardware that's being tested on board the International Space Station. Researchers are looking into using 3D printing technology to manufacture biological materials in microgravity. Now, that would allow cell growth to happen in 3 dimensions, and it potentially could get around the problem of rejection of the immune system rejection of the donor tissue if the patient's own cells were used to grow the new organ.
Cutting-edge biomanufacturing aboard the International Space Station. Presented by Science at NASA. Most likely, you're aware of 3D printing, which allows you to design and produce one-of-a-kind pieces for a variety of purposes. But what if you could use that same technology to manufacture biological materials, like new tissue or blood vessels? Welcome to the world of 3D biomanufacturing, a cutting-edge practice on Earth that is being tested aboard the International Space Station, or ISS. Dr. Mike Roberts, Deputy Chief Scientist at the ISS U.S. National Laboratory, explains why the space station is critical to biomanufacturing's future. We've been able to grow cells in a lab for well over a century, but gravity limits that growth to 2 dimensions. Cells can grow outward, but not up and down like they do in the human body. Also, lab cells are often in contact with the glass or plastic that contains them. But aboard the space station, our experiments will be conducted in microgravity. That allows you to build your cell models in 3 dimensions, without being confined to the bottom of a dish, or unable to grow in contact with lots of other cells. Biomanufacturing imagines the ability to someday grow a viable human organ. Organs are composed of specific tissue intersected by blood vessels. Most organs and thicker tissues in the body have a rich, complex network of blood vessels that provide nutrients and remove wastes from the living cells that make up the tissue. We currently lack the ability and the tools to engineer these highly branched living networks of vessels inside layers of tissues on Earth. Another medical advantage to manufacturing biological parts in space is the potential to bypass the body's immune system. Today, organ transplants from donors are prone to rejection because the patient's body perceives the new organ as a foreign object, and their immune system tries to attack it. But with the ability to grow tissue in space, a person could conceivably have their own cells used to make their new organ, which might avoid the body's rejection. 3 different types of biomanufacturing facilities will be tested aboard the space station. 2 of them perform in a manner similar to a standard 3D printer. They extrude cells in layers to build tissue. The 3rd type uses powerful magnets to position the cells in place. Each of these 3 different approaches to bioprinting in microgravity will be available to medical researchers seeking to better understand how to engineer tissues and organs for use in repairing injury and curing disease on Earth. As Dr. Roberts notes, the 3D bioprinters represent cutting-edge technologies that could clearly benefit health outcomes on Earth. I think the ability to manufacture a fully functioning human organ will take some time, maybe a decade or more, but the knowledge we'll acquire to get there will also create interim benefits as we learn more about cell regeneration in space and its application to humans on Earth. For more inside information about studies inside the station, visit www.nasa.gov/ISS-science. For more on science happening on, around, and beyond our planet, go to science.nasa.gov.
The International Space Station provides a working laboratory for astronauts in the microgravity environment, and solar energy is a key element in keeping it running. Astronauts rely on this renewable energy source to power the machines they need for their science work, and to power the ones they need for their survival. In this demonstration video, astronaut Ricky Arnold explains the process of generating power from the station's solar arrays to produce electricity for astronauts as they orbit 250 miles above the Earth's surface.
Welcome aboard the International Space Station. I'm astronaut Ricky Arnold, and I'm currently at one of our human research facilities on ISS, where you can see centrifuges, laptops, and other scientific equipment. Across from me is another one of these experiment racks, where you can see ultrasound imaging, more laptops, cameras, other equipment, all stuff that requires electrical power. In fact, we have so much equipment for science and life support that our electrical system has about 8 miles or 13 kilometers of wiring to make it all work. So where does this energy come from? Let's have a look. From here in the cupola and through other windows, you can easily see the solar arrays soaking in the sunlight. They are massive. These 4 solar arrays are made of solar cells, which are purified chunks of the element silicon. Together, the solar arrays contain a total of 262,400 solar cells and cover an area of about 27,000 square feet, more than half the area of a football field. That's huge. When the station is in sunlight, the solar arrays produce about 60% more power than we actually need during the daytime. That extra power goes directly to charging our lithium-ion batteries. Now, those batteries are essential because they provide the power we need during the 16 night times we have per day here on the space station. The energy our solar arrays can produce is enough to power 40 homes, and we can maximize the power we generate by rotating the arrays in 2 axes, one like a windmill to track the sun through the course of the day, the other to track the sun's inclination, or its angle in the sky. The space station's electrical power system uses direct current to provide energy for our laptops, lights, water recovery system, and science experiments. Thanks for coming aboard today. Now back to Earth.
For all the years that men and women have flown in space, they've taken pictures out the window of their home planet. You saw some of them there in that feature. Well, those pictures, they're amazing. They're remarkable. But for the folks who took the pictures, it's still something of a strain for them to convey to the rest of us Earthlings just how miraculous that view really is.
I had looked at pictures on social media and pictures in NASA archives of the Earth so many times, I actually started to get worried. What if I get up there and it's just like the pictures? I mean, that's going to be weird if that's the thing where I'm like, oh, it looks just like the pictures. I'm ready to go home now. And then on the Soyuz, my launch vehicle launched with the Russians. And on my Soyuz, when I first got a chance to look out my little window, which is about right here at the Earth, there's something about looking out a round window at the curvature of the Earth that makes it just more pronounced and really makes it have a huge impact. I just had this feeling like I was way up high looking down, and we were over the ocean, and the blues that I saw, it was ridiculous. I'd never imagined in my entire life getting to see something that beautiful. It was so foreign for the human mind to look at that, to see that total black of space, to see the Earth highlighted that way. And then I got to see a sunset. I had one piece of paper, it had a picture of my kids on it, and a few of my flight data file burn times on it, but I just took a pencil and I drew like 15 curved lines, and I just wrote light blue, darker blue, pink, purple, dark purple, all the way down to the surface of the Earth at sunset, because the scale of looking at a sun refracting through the atmosphere, it blew me away, and no picture captures that. There's no high enough dynamic range of a photo to capture what the human can see. So that first look outside completely sidelined me. I had a GoPro, and I made a recording to my brother of, no matter how much it costs in the future, come do this. You have to come do this. I mean, it's amazing. Over my 6 months in space, getting to look at the Earth every single day, it shows you something different. Every day it shows you that it's alive. It's a being just like we are. We're guests on this planet, and it is It's our mother, it's our father, it's our starship cruising around the sun in the middle of the solar system. There was never a moment that I looked out the window and didn't immediately grab a camera to take a picture of something that our planet was doing. It always surprised you. It's always magnificent. I'm a pilot, I'm not a scientist, I'm not a psychiatrist, I'm not a poet, but certainly when you're in low Earth orbit, looking down at the Earth, it doesn't matter if you're a physicist, a school teacher, a stay-at-home parent, or maybe you just backpack for your whole life. If you look out, you're going to have a magical experience in your own way, for certain.
Now, in the meantime, NASA's Artemis program is underway. Now, Artemis is going to return Americans to the moon by 2024 and help us get ready to go on to Mars. Knowledge of the geology of both locations is going to be very important. Earlier this year, the next to last man on the moon, Apollo astronaut Harrison Schmitt, joined astronaut candidate Jessica Watkins in the Johnson Space Center's Moon Rock Lab. These two geologists got together to discuss how what we learned from Apollo is going to inform our efforts in Artemis.
All we did was sample of both sides, but wouldn't bet on it. Okay, I just got a chunk of that side.
Just they have what I consider one of the most
Can you talk about kind of what went into your sampling strategy and how you chose which samples to bring back?
The idea was to get as broad a spectrum of new samples as we possibly could, and that turned out pretty well. And in fact, we sampled at least what we call melt ejecta from 3 major basins, maybe 4. We sampled fragments that almost certainly came from the deep mantle of the moon. We didn't know that at the time. That's only recently that we figured that out. And that we also then added to our broad knowledge and history of these volcanic eruptions that have occurred on the moon over time. Now, when you go to the moon on the way to Mars, Jessica, that education I think you're going to get on the moon will be very relevant to Mars. But Mars, of course, does not have that micrometeorite impact environment that we have on the moon, because it has a small atmosphere, about 1/100th of that of the Earth, and that filters out the small impact. The main weathering process on the moon are these micrometeorite impacts and solar wind spallation of the surface. Solar wind's made up of high-energy particles, so they actually erode the surfaces of rocks as well as change the character of the debris layer on the moon. On Mars, the dominant erosive force is wind.
Yep.
And so if you're used to studying geomorphology here on Earth that involves wind,
you're in good shape.
you can learn a lot about what you're going to see on Mars. But all of that comes from studying the moon.
Right.
If we hadn't had the moon, we wouldn't understand this early history of the Earth, or even speculate about what it might be, speculate intelligently anyway, about what it might be.
If you'd like to get another look at any of the features we showed you today, you can. You can check us out on YouTube or on Facebook. There are the addresses right there in the little blue box. While you're there, be sure to look around. You will find lots of other cool stuff about NASA and America's human spaceflight program. If you're out on the internet anyway, you could also check out Houston, We Have a Podcast. That's where we talk to folks about their work in all aspects of space exploration, including human space exploration. We post new episodes every Friday, and today we share a special opportunity we had earlier this year to talk to one of the 4 Apollo moonwalkers who's still with us. On this day, today, before the 47th anniversary of the launch of Apollo 17, Gary Jordan talks with the second to last man on the moon, Harrison Schmitt. Yeah, the same one you just saw. What a coincidence. Go to nasa.gov/podcasts for today's episode. It's where you'll also find all our previous episodes and the full library of all of the NASA podcasts. all of which you can also listen to on Apple Podcasts, Google Podcasts, and SoundCloud. This is Mission Control, Houston.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Hello, welcome to NASA Science Live, your chance to go behind the scenes at your space agency and get your questions answered by NASA scientists and experts. I'm your host, Greg Hautaloma, and today we're here at the American Geophysical Union Conference in San Francisco. It's one of the largest conferences in the world, and people are presenting papers on all kinds of topics. We're going to learn more about our OSIRIS-REx mission, NASA's first mission to get a sample from an asteroid and return it to Earth. We want you to ask your questions to our NASA experts by using the hashtag AskNASA at Twitter and on Facebook or in the comment box wherever you're watching this. I'm going to head to the NASA booth right now to meet those experts, so please join us there, but first watch this video about OSIRIS-REx.
On September 8th, 2016, in Cape Canaveral, Florida, OSIRIS-REx began its journey, NASA's most ambitious sample collection attempt since the Apollo program. After 2 years, including a gravity assist from Earth, this spacecraft arrived at its destination, asteroid Bennu. As OSIRIS-REx drew near, Bennu grew in detail from a few tiny pixels to a surprisingly rugged world, littered with giant boulders. This spacecraft has used its instrumentation to map the asteroid from all sides, mapping it in unprecedented detail. The mission team has been analyzing the data, scouring Bennu's surface to select the best sample site. Now, with just months to go before sample collection, the team has narrowed its target down to 4 potential sites.
Hello, and thank you for joining us in the booth here at AGU, the American Geophysical Union, for this special edition of NASA Science Live. Today, we have a big announcement from the OSIRIS-REx mission. OSIRIS-REx is NASA's first mission to retrieve a sample of an asteroid and return it to Earth. The mineral particles that make up Bennu, the asteroid that is being orbited by OSIRIS-REx, they could be as old as the solar system itself. Dying particles from stars could have formed the planets and our own sun. And now we're going to get a sample from that asteroid and return it to Earth. And we're going to find out from where today. We're going to get maybe upwards of 30 sugar packet samples worth. So it's very exciting, and I'm really pleased to have here today some mission team members. So please let me welcome Danny DellaGiustina
Hey, Gray.
and Mike Moreau, and they're going to tell us a little bit more about the mission and the challenges and where we go next. So I guess the big obvious question is why? Why did we want to study Bennu?
Yeah, that's a great question, Gray, and I'm really excited to talk about Bennu and the mission ahead of this announcement. So Bennu is a near-Earth asteroid, and that means its orbit is in close proximity to our own planet, and it was fairly accessible for us to send a spacecraft there, so that's one reason. But because of its close proximity to planet Earth, it's also a potentially hazardous object, and so by sending a spacecraft there and flying in formation with Bennu for over 2 years, we're going to get a much better sense of Bennu's orbit and be able to better predict whether or not it is a hazard in the coming decades and centuries. But finally, Bennu is composed of water-bearing minerals, and that was a discovery we made very early on in the mission. And there's early indications that it might have organics as well, so we think that Bennu looks a lot like the objects that might have delivered the precursors to life to early Earth. And so it's also exceptionally scientifically exciting to be in orbit around this surface.
Wow. I can't wait to find out more about it. I know it gave us a lot of surprises. Do you want to tell us a little bit more about that, Mike?
Yeah, so one of the biggest surprises when we saw what Bennu looked like is what's on the screen here. It is just covered with rocks. So on the table next to Danny is a model of Bennu that was created before we arrived, and in many ways Bennu met our expectations of its general shape, its spin axis, and its mass. But the fact that it's just so covered in large boulders and such a dramatic surface was a big surprise. And that caused us to reevaluate the whole process and the data set that we would use for site selection and make some new improvements to the capabilities of the spacecraft so that we could actually go down to the surface of this asteroid.
Wow. And we'll talk about that a little bit more later too. Tell us what Bennu can tell us about other asteroids in general. I know there's a lot out there.
Yeah, so Bennu can tell us a lot about other asteroids in a number of ways, but something that sticks out is earlier this year we discovered Bennu is what we call an active asteroid. And so that means there is mass that is actively being ejected from the surface of Bennu. And we have seen similar activity on larger asteroids through telescopic observations, but we haven't seen this sort of activity at the low energies that we observe on Bennu. So it's giving us a better sense of the range of active asteroids that exist in the solar system. Just to give some perspective for the range of energies that we see these sort of ejection events, if you were to snap a cracker in half, the energy release there is comparable to the ejection events that we're observing on the asteroid.
Wow, there is a lot going on at that rock. So we want to get your questions, and they are already coming in, but if you use the hashtag AskNASA at Twitter or Facebook or in the comment stream, wherever you are watching this, we're going to try to take as many of them as we can during the program. So let me get to the first ones of those. Ankur on Twitter asks, how big is the asteroid and does it have a particular orbit?
So I can go ahead and answer the first part. So Bennu is about 500 meters in its longest dimension, and to give some perspective, that's about the size of the Empire State Building, so about 100 stories. Do you want to answer the question about the orbit, Mike?
Yeah, Bennu is in a near-Earth orbit, so it's in an orbit around the Sun that is very close to the Earth's orbit, and it actually crosses the Earth orbit. And as Danny alluded to, that's one of the reasons Bennu is such an interesting object for us to study in this mission. We are interested in precisely studying its orbit and how that orbit evolves over time to understand how close it might come to the Earth.
Okay, appreciate that. So, can you tell us where the name OSIRIS-REx comes from?
So OSIRIS-REx is, as our principal investigator likes to say, an awesome acronym. So all of those letters have individual meanings. It stands for origin, security, spectral interpretation, resource identification, regolith explorer. So there's a lot there.
That's pretty good. Okay, well, I hope that answers that question. Let's see what we got. Another one. Gemfef on YouTube asks, what are you looking for when you go to the sample site? When you're searching the sample site, what are you looking for?
Yeah, so the primary thing that we are looking for is the presence of sampleable material. We're also very interested in whether or not the site is safe. But from my perspective as a scientist, I'm very interested in whether or not these sites might have organic material or things that we think are similar to the precursors to life that were eventually delivered to Earth. Is there anything you want to add about the safety?
From my perspective, our number one goal is to keep the spacecraft safe while navigating down to these potential tag sites. And so we're interested in the fact that some of the sites have very large boulders in the vicinity of them and smaller rocks within the area we're trying to contact that could be potentially hazardous to the spacecraft. So we've had to take precautions in order to keep the spacecraft safe.
Okay, well, I want to thank you both. That's been really fascinating. And now we've got a video that we're going to show you some of the surprises at Bennu that they were talking about. That's going to go into greater detail about it. So let's watch that right now.
In late 2018, as NASA's OSIRIS-REx spacecraft neared its target, Bennu, the asteroid grew in detail from a few tiny pixels to an incredibly high-resolution image. OSIRIS-REx confirmed the asteroid's basic shape, which was originally observed in 1999 by ground-based radar at Arecibo Observatory. What scientists didn't expect was just how rough and boulder-filled the asteroid would turn out to be. While it can be difficult to fully grasp Bennu's unfamiliar surface, it's helpful to understand the scale of what you're seeing here. In this image, the brightest boulder is the length of a horse, and the large boulder in this image is the width of a soccer field. Another challenge for the mission is the asteroid's small size and weak gravity. This means that OSIRIS-REx needs to fly daringly close to the surface in order to enter into orbit. With its orbital A phase, OSIRIS-REx successfully entered the closest ever orbit for a spacecraft, setting a Guinness World Record in the process. Then, 6 months later, it beat its own record during its orbital B phase and approached to within a few hundred meters of the rocky surface. Because OSIRIS-REx flew so closely over the surface during orbital B, the team was able to map the topography and shape of Bennu better than we have our own moon. In addition to mapping asteroid Bennu, OSIRIS-REx plans to collect and return a sample back to Earth. To do that, the spacecraft will carefully tag the surface of Bennu. The OSIRIS-REx team has selected 4 possible sample sites for the mission: Osprey, Kingfisher, Nightingale, and Sandpiper. The spacecraft has been closely imaging these sites from different angles to select the best touchdown spot for OSIRIS-REx. What was originally envisioned as a smooth and easy touchdown on Bennu's surface has become a complex endeavor to tag a small, crowded space on the asteroid, an area no larger than a few parking spots, by mid-2020. The OSIRIS-REx team has already pushed the boundaries of scientific exploration, going from ground-based radar images all the way to being a few hundred meters from the asteroid's surface, and is now mere months away from a sample collection attempt.
All right, well, that video gave us a lot of perspective on just how hard it has been to explore Bennu once the spacecraft got there and all the surprises that the team encountered. But we are now getting ready to select that sample site and tell the world about it. And we've heard a little bit about Bennu and where it is, what it looks like, and now we're going to get a little bit more into the why of why we do this. I'm pleased to be joined by Dr. Lori Glaze, who's head of the Planetary Science Division at NASA headquarters.
Hi, Gray.
Welcome, Lori. So, tell us, why do we do sample return?
It's a great question. So we've been observing Bennu now for about 20 years, first observed using ground-based telescopes, and then over that 20-year period we've continued to observe the asteroid using ground-based and space-based observations, and then over the last year, of course, we've been able to observe using the OSIRIS-REx spacecraft, but all of those measurements and observations are remote sensing observations. They're done from a distance, and there really is just no substitute for being able to actually pick up some of that material from the surface and bring it back to Earth. By bringing it back, that allows us to use the full capabilities of all of our state-of-the-art technologies and laboratory facilities to analyze those samples, to answer some of the really big questions that we have that Danny was talking about when she was sitting here. And not only can we answer those questions using our facilities today, but we'll actually preserve most of the sample for all of the generations to come that they can then use new facilities and new instrumentation that we haven't even dreamed of yet.
Wow, that's going to be amazing. So, what in particular do we think we'll learn from Bennu?
So, Bennu is actually going to address several major questions, and three big ones in particular. First off, you heard, or you said earlier, that Bennu we think is a really old object that's really a remnant and preserved from the very earliest parts of our solar system. So by looking at those samples, we'll get insights and information telling us about what conditions were like when the solar system formed. And then Danny talked about how we think there are hydrated minerals and perhaps organic molecules on the surface. And by looking at those, we'll better understand how those types of materials were delivered to Earth and perhaps were the seeds for how life actually began to form on Earth back in the earliest times. And then finally, it's also going to help us better understand what types of resources might be available on these asteroids that are out there, that as we start to take human exploration beyond the moon and start to go other places, there may be resources there that may be of use to us in the future.
Well, these are some really big questions. And I know OSIRIS-REx is a unique mission, but there are other missions in place going forward to get samples from other places, building on the Apollo moon rocks we have and going to Mars and so forth. How does that whole field fill in this?
Absolutely. So, of course, the Apollo missions were the first missions to actually bring samples back. We get natural samples all the time, of course, with meteorites that come through the atmosphere. But the Apollo missions brought those samples back. We're still analyzing those samples today, 50 years later. We just opened up some pristine samples a few months ago, or just trying to look at those with our new technologies, as I was saying. But we also are working right now with the Japanese Space Agency on their mission to visit another asteroid called Ryugu, and next December they'll be returning some samples from Ryugu that we'll be able to study another asteroid in comparison with Bennu. And then Japanese Space Agency is also planning a mission to the Mars moon named Phobos to bring back samples from there. And of course, we, NASA, next summer will be launching the Mars 2020 rover, which will land in Jezero Crater, drive around, and collect samples from Mars that will be left on the surface for eventual return by a Mars sample return mission.
Well, there's a lot going on in this area. Thank you so much, Lori, for that perspective. Really appreciate it.
My pleasure.
Well, now we're going to bring up the man with the answers. Dante Loretta is the principal investigator of OSIRIS-REx, and his team has been working round the clock since OSIRIS-REx arrived at Bennu last January 1st, and they discovered all those surprises we've been talking about. And he's going to give us an overview of how they narrowed down the multiple candidates for site selection and then announce the real one. So Dante, tell us about the whole process of narrowing these down.
Yeah, thanks, Gray. As you can see from the map of the asteroid behind us, when we first got there, the most obvious feature that we saw were these abundant, very large boulders, and overall a rough and rugged surface, very different than what we designed the spacecraft to sample. We were looking at sampling areas that were 25 meters in radius across, and quite honestly, I thought it was going to be obvious from the first images where the sample regions were and that it was going to be a straightforward site selection, and it was nothing of the sort. So the first thing to do was to complete the global characterization of the asteroid. We used our camera systems, we have laser altimeters for getting the topography, and we have several spectrometers for analyzing the mineralogy and the chemistry. And the science team did an amazing job of synthesizing all of that information and making a whole series of maps of the asteroid's surface. And then we went through several different ways to characterize it. We had the team looking at the imagery and the other data to pick areas that looked sampleable. We used machine learning algorithms. We also wrote specific software to find flat areas on the asteroid surface. And we also crowdsourced some of this information out to get the community involved in helping us select the sites. After that process, we actually had 50 different areas on the asteroid surface that looked like they might be interesting for us. And so I set it up kind of a tournament-style bracket. We ultimately got down to our Sweet 16 and then the Elite 8. and to the final four where we are right now, about to crown the champion and the runner-up of this process.
All right. Well, I understand you have some really cool videos of those final four sites. So why don't you go over them with us?
Yeah, let's take a look at the final four candidate sample sites. So we're going to start out with the Osprey crater. This is about 20 meters in diameter. One of the key features is the big flat rock that's 5 meters long. We call that 12 o'clock rock because it's almost pointing due north, and it kind of sets our orientation for us. It does look like it has some fine-grained sampled material, especially right towards the central region and in the trough or the ridge, beyond the ridge to the east there. But it is a kind of a rough and rugged surface, and so we do worry that it might be a little more challenging to ingest those 2 centimeter sized particles from its interior. But overall, the surrounding area, because it's up on kind of a hill, it's relatively free of hazards that we might fly into on the back away from collection. Let's take a look at the next one. This is the Kingfisher site. So this is similar to Osprey in that it's in an equatorial region, and we like the equator because the navigation team has higher accuracy when we're targeting equatorial sites. This is a smaller crater, about 10 meters in diameter. One of the most intriguing features are the 2 smaller craters that we in fact call the Mickey Mouse ears. Those look like the best, finest grained sampleable regions on the asteroid, but they're really small, on the order of 2 meters across, and we know we can't get the spacecraft into a spot that tight, but the hope was that that same kind of fine-grained material was accumulating in the center of this smaller crater. If we take a look at our next candidate, this is the Nightingale crater. So unlike Osprey and Kingfisher, this one's at high latitude up in the northern region of the asteroid. It's a crater about 20 meters in diameter. It's characterized by a lot of apparently fine-grained material. We do see a few large boulders that look like they've rolled down into the lowest depression over here on the right side of our image. And the most characteristic feature for me is this large wall of tall rocks. That does represent a potential hazard to the spacecraft, because when we make contact with the surface, the only thing that touches it is the sample collection head at the end of a long robotic arm. That may tip over a little bit, and we back away at whatever angle we've tipped to, and we're concerned that we might fly into some of those hazards. So let's take a look at the final site. This is the Sandpiper site. So this is also a high latitude site, except it's in the southern hemisphere of the asteroid. And unlike the other 3 sites, it's part of a much larger crater, about 50 meters in diameter. And what's really interesting here is the site itself is on one of the slopes of the crater wall. And it looks like there's a whole series of boulders that are kind of rolling down this terrain like a slow motion landslide. But the Sandpiper site appears to be shielded from that process by this large rock off to the south. So there's a whole swath of the crater wall that's relatively free of boulders and appears to be dominated by that fine-grained sampleable material.
All right. Well, those all look like great candidates. Well, you've seen them all now, and some of those space rocks you're seeing right now are going to be brought back to Earth. That's pretty exciting. So, Dante, do you want to tell us which one you've picked?
I will. So I'll say that just thinking that we're going to get this sample back to Earth sends chills down my spine. So the winner of the OSIRIS-REx Site Selection Championship is the Nightingale site.
All right. Make some noise, audience.
Thank you. So we recognize that this does have some hazards around it, and so we are doing a lot of work to make sure that we're targeting the safe regions, but this one really came out on top because of the scientific value. The high latitudes means that it stays relatively cool, and the primary objective of OSIRIS-REx is to bring back organic material and water-bearing material from the early solar system, and being in those high latitudes we think gives us the best chance to preserve that kind of material. Since we are dealing with a site with some hazards nearby, we have put some safety mechanisms onto the spacecraft. The spacecraft can actually tell if it's coming down onto a hazardous region and wave off and abort and fly away, fire thrusters and fly away from the asteroid. That may disturb the surface and make that region unsampleable. So we also have a backup site. The runner-up is the Osprey site. That's the 20-meter crater near the equator. We know we can get in there. It doesn't have the hazards that Nightingale does, but it also may be more challenging to collect a sample, but we think the lower hazards makes it the right choice for the backup.
Well, thanks for that, Dante. We do have a bunch of questions flowing in from social media. Again, use the hashtag AskNASA if you have one. And let's just go right to someone from in our audience. Aaron in the audience asks, what is the biggest challenge of the site?
So the biggest challenge of the Nightingale site is those large boulders that are off on the eastern edge of the crater, because that tallest one, I colloquially call it Mount Doom because it has the classic kind of peak shape that we're familiar with from the literature. That's about 7 meters tall, and then when you're down at the bottom of the crater, that's another 3 meters. So we're talking 10 meters or 30 feet. So it's a substantial building-sized obstruction, and we're trying to get into a crater that's on the order of a few parking lot spaces wide. So we are doing a really tight job parking that, and we're aware that we have hazards around us. So precision navigation to that sampled material is our biggest challenge.
Wow, well that's going to be some amazing engineering. Well, that's all the time we have for questions right now with Dante, but keep sending them in, and thank you so much, Dante, and congratulations. Thank you. So right now I'm going to invite Mike Moreau back to the stage, and he's going to talk a little bit more about the engineering that makes this amazing sample return possible. We have an instrument aboard OSIRIS-REx called the TAG-SAM, which is actually going to ingest the sample in a very unique way that Mike's going to explain, and then cache that sample and to return it to Earth later after we get it. So welcome back, Mike.
Thank
you. Tell us a little bit about the challenges of the sample collection using this instrument.
Yeah, so you can imagine when the OSIRIS-REx mission was being formulated, engineers had a really interesting design challenge, and that's how do you collect a sample from an asteroid millions of miles away using a robotic spacecraft. And the TAG-SAM is the innovation that our partners at Lockheed Martin came up with to do just that. The TAG-SAM, as is shown here in full scale, and it actually sits at the end of a robotic arm at the end of the spacecraft. So the TAG-SAM is the only piece of the spacecraft that will touch the surface, and in doing so, once contact with the surface is detected, there will be a nitrogen gas bottle that is fired, which stirs up the surface underneath the TAG-SAM, churns up some of that fine-grained material, which will then be captured in the outer ring here. Once the spacecraft has been in contact for just a few seconds, it will fire its thrusters and back away, hopefully with the sample in hand.
So there's so many contingencies potentially here. What happens if it gets too close and it realizes it's a hazard or there isn't enough to even sample?
Yeah, so Dante alluded to this in his remarks. We've had to make some changes to the capabilities of the spacecraft to allow us to navigate into a site like Nightingale. And we've implemented something called a hazard map, which will be uploaded to the spacecraft. And then the onboard knowledge that the spacecraft has of where it's coming down, if it detects we're coming down on one of these hazards or too close, it will back away and we'll have a chance to try again.
Wow. Well, that's a good backup. What happens once you do get the sample collected? What happens to it?
So once we back away, the next couple of days will be spent assessing the health and safety of the spacecraft after contacting the surface and trying to figure out if we have a sample. The two primary ways that we'll figure out if we have a sample, one is just simply imaging the TAG-SAM with the cameras on board the spacecraft. We'll be able to see if there's material that's captured inside the ring. The other technique that we're going to use is called the sample mass measurement. And we will be actually spinning the spacecraft in a little pirouette, and that will help us determine the mass of sample that's at the end of the arm.
Wow. So you're an engineer. We have a question from Andrew Siegel on YouTube, wants to know, how do you decide the maneuvers the spacecraft has to do, and how do you assess your options in such a tight space?
That's a great question. The navigation team and our Lockheed Martin team are spending many hours designing the trajectories that have allowed us to fly in proximity to Bennu and collect all of the images that are shown in this mosaic on the screen. And they're right now that we've selected the Nightingale site, doing the final designs of the trajectory that will take us from orbit down to the surface and contact the sample. And there's been a lot of work already done to determine those trajectories and how accurately we can actually contact the surface.
At Benjamin on Twitter wants to know, how is the team's work changing now that you've got the focus, you know where you're going?
The team is incredibly excited now to have the site selection decision, and Nightingale is an exciting site to go into because of the challenges it's posing. And the team has really risen to the challenge, both to come up with how we would make the decision about the best site, but also to convince ourselves that we can actually get there and navigate the spacecraft successfully. So the team, I think, is really excited to be able to move forward and put all of our attention towards tagging at the Nightingale site.
Great. We've got just a couple more real quick here. Maybe, I'm not sure if you'll be able to answer this yourself, but Lucy on Periscope wants to know, are there going to be precautions for quarantine once this is brought back?
That's not my expertise, but there will be great care taken when the sample returns to the Earth. It will enter the atmosphere in a small sample return capsule that will land in the Utah desert, and there will be a huge effort to recover the capsule and then transport it to Johnson Space Center, where there are facilities in place to curate and make the sample available to the public for analysis, for scientific analysis.
Thanks so much, Mike, and I want to thank everybody who was on the show today. That's all the time we have right now, but please continue to go to nasa.gov/OSIRIS-REx and keep following the mission. It's only going to get more exciting as it gets closer and does these sample return maneuvers and then gets the sample back to Earth later. So that's all the time we have for now. Until next time, let's go play tag.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Throughout human history, people have always worked to harness power to better their lives. Early on, our forebears developed rudimentary machines driven by wind, animals, and water to run these devices. These machines were state-of-the-art for their time, but as with all things, new ideas began taking shape that changed the landscape of how power was developed. Eventually, new machines, fueled by gas, steam, diesel, and coal became the norm, and are, to this day, still the primary way we supply our buildings, cars, and overall lives. And the demand is not slowing down. In recent years, power usage has increased exponentially. So planners have been looking at new technologies and ideas to help bring us out of the 20th century mode of power generation and into the future. Not surprisingly, NASA personnel are part of the core wave of engineers and researchers who are looking at ways to change how we develop power. While some of their ideas will have Earth applications, the bulk of their study is finding ways to improve how power is used and developed aboard spacecraft. This work will help us move past our current methods of power generation in space, allowing new and exciting technologies to come online that could be the disruptive force we need to advance spaceflight. Coming up on this episode of NASA X, we will follow researchers from NASA's Space Technology Mission Directorate's Game-Changing Development Program as they attempt to transform the way spacecraft of the future are powered. We will see how these changes can increase speeds, be more efficient, be a fraction of the size, and potentially cost much less than conventional methods. And with these new technologies in place, they could have the potential to move us even closer to the goal of exploring deeper parts of space. Since the beginning of spaceflight through today, there have been huge improvements in the technology surrounding vehicles that travel in space. As an example, the flight computers that flew humans to the moon in the 60s and 70s were state-of-the-art then, but had less processing power than a cell phone of today. In the more than 40 years since Apollo, there have been enormous changes in every aspect of spaceflight, not the least of which is in the fields of power and propulsion.
Main engine ignition. 4, 3.
Often these fields get overshadowed by flashy mission hardware and instruments. But without these core elements in place, no mission would ever make it off the ground. Because power and propulsion are so important, NASA's Space Technology Mission Directorate is taking steps to continue improving our understanding by ensuring that next-generation technologies will work as expected and help move us past our current methods of travel. They have broken power and propulsion up into two major categories. The first is in the field called in-space propulsion, which refers to the development and testing of different types of thrusters that are used in space. While the second area is called space power, which studies how power is generated on orbit, such as solar arrays, for example, and also how we store energy with batteries and fuel cells. To understand what future missions will be like, we first have to look at the space environment and how missions of the past have worked. Because of Earth's gravity and atmospheric conditions, we still need those big, powerful rocket engines that burn chemical propellant to get us into space. Once in space, current missions and those of the past mix an oxidizer with the chemical propellant for a short but powerful push toward the given destination. This burn lasts only a few minutes, then shuts down. Because the craft is not fighting gravity or atmospheric conditions in space, it just coasts the rest of the way without losing any velocity. Although this practice still works well, researchers in recent years are looking into new ways to get to destinations. One of the most intriguing ideas on the table is something called solar electric propulsion, or SEP. Helping to lead this effort for NASA's game-changing development program is principal investigator Chuck Taylor.
The new idea is what we're really focusing on now is electric propulsion. And that differentiates itself from chemical propulsion in that rather than combusting a fluid and getting a managed explosion, if you will, you're basically exciting ions and getting an electron and an ion stream leaving the end of the engine, and that's how you get your propulsive force.
This form of propulsion is intriguing because it uses energy captured by the sun. It relies on the acceleration of ions using electricity generated by solar arrays instead of the chemical energy stored in the propellant itself. It is very attractive to NASA planners because by using the sun's energy in the process, considerably less propellant is being brought into orbit, which reduces launch mass and cost. An SEP system is usually considered to consist of the large arrays that generate electric power, the power processing units that convert this power, and the thruster, which uses the electric power to ionize the inert propellant and accelerate it out of the spacecraft to generate thrust. Each of these elements are being studied, with one of the most important pieces being the large solar arrays themselves. A big challenge facing planners is how to get enough power to complete missions.
We're creating a set of solar arrays that are about 2 times the size of solar arrays that are in use today. We're talking about generating on the order of 50 kilowatts of prime power, which was a substantial step up from what is used in the commercial industry today or any government satellite. The biggest hurdle we have to overcome is the mass of those arrays and the stowage volume of those arrays. If you think about it, the space station has arrays that are a rough equivalent of what we're trying to produce, but it took upwards of 10 shuttle missions to get those arrays on orbit, and we had to have astronauts actually go out and put them together and assemble them. We're trying to make arrays with just as much prime power, but be able to be stowed on one rocket launch and have them deployed autonomously.
Because these new arrays are so large and so unique, testing them will take a very special facility. Just outside of Sandusky, Ohio, is one of the most important testing chambers in the world. Called Plumbrook Station, this NASA facility is home to the world's largest space environment simulation chamber. At just over 100 feet wide and 122 feet tall, it is possible for researchers to perform full-scale tests of spaceflight systems in a vacuum and temperature environment ranging from low Earth orbit to deep space and planetary surface conditions. You may have seen this facility before if you saw the first Avengers film. But the real-world applications that NASA is developing here have the potential to be more revolutionary for future space missions than anything Hollywood could think up. NASA's Carolyn Mercer walks us through the facility to explain how next-gen solar arrays will be tested.
This is the Space Power Facility at NASA's Plumbrook Station. It is the world's largest vacuum chamber, and we are going to bring one of our solar arrays right in here to determine whether or not it really is going to be able to autonomously deploy in the conditions that simulate space, namely a vacuum and hot and cold temperatures. Just like a tall ship, we have masts that are going to be used to hold our cryo shroud and booms and spreader bars to attach to the vacuum chamber here. The cryo shroud itself is called that because it is going to be cryogenically cooled to get us to minus 60 degrees Celsius and then warmed up to plus 60 degrees Celsius. This cryo shroud is big. It's 40 feet in diameter and 40 feet high, but it's big enough to hold our about 30-foot diameter solar array wings.
As Carolyn mentioned, NASA will be testing these new 30-foot solar arrays in this facility. Of course, solar arrays in space are not new, having been used for decades to power spacecraft. But if we are to move past low Earth orbit and into deeper space, new technologies like improved solar arrays will need to come online.
Solar arrays are flying right now. Commercial satellites are flying solar arrays. And the International Space Station flies solar arrays as well. For comparison, the new arrays that we're building right now are going to be about 20 kilowatts of power. They'll provide about 20 kilowatts of electrical power. And they're about 100 meters squared in size. So for comparison, for a single solar array wing on the space station, you'll get about half again as much power, so about 30 kilowatts, but it's 3 times bigger, much larger area. And for a commercial satellite using solar arrays, the state-of-the-art is about half the power, about 10 kilowatts. But the important thing is that the state-of-the-art uses rigid panel construction, we call it. So the solar cells themselves are fixed onto like a honeycomb structure. We're not doing that anymore. We have this really novel, flexible blanket technology so that combined with high-efficiency cells and lightweight structures, we can get very large arrays. So for instance, we're building about 20 kilowatt sized wings right now. You put 2 of them on a spacecraft, you get about 40 or 50 kilowatts of power. That will enable you to do exciting missions like the asteroid redirect mission. The very same design can be scaled up to, let's say, 250 or 300 kilowatts, and that would allow us to send people out to an asteroid. And then the same technology can be scaled up yet again to maybe 800 kilowatts, and we can send people to Mars. So I'm really excited about this technology because it is the stepping stone for how we're going to explore space differently. And this matters a lot because solar electric propulsion, for which these wings are, we're developing, it's a much more economical way to explore deep space with people.
The solar arrays address the solar and electric part of SEP. But what about the propulsion? Here at NASA Glenn, researchers are working on new thrusters that will work in concert with the arrays to power these new devices. Thrusters like these use the electricity captured by the arrays to ionize the fuel, which in this case is xenon, to produce the thrust that pushes the craft forward. Although this technology has been around for decades, the more than 200 satellites already using them only have very small thrusters. NASA needs much larger devices to move us further into space, so there is a big push to build these devices.
Here we have a 12 kilowatt Hall thruster. Hall thruster technology is also being invested in by Game Changing to provide high fuel efficiency, higher power, higher thrust capabilities for in-space propulsion. So this is about the same size as the thruster that's being developed within the Space Technology Mission Directorate, a little bit larger in size. The improvements that we're trying to make by studying these devices is increasing lifetime, an order of magnitude, increasing power, and increasing the exhaust velocity of the ions. That exhaust velocity is a higher specific impulse, and it provides better fuel economy, essentially. And what we're trying to do here, under the Game Changing, is really push on three critical areas. The power level, so 2 or 3 times the current state-of-the-art power level. Higher exhaust velocity, 50% higher exhaust velocity results in higher fuel efficiency. And 3 or 4x the operational lifetime. So geostationary ComSats, they have lifetimes for the spacecraft on the order of 10 to 15 years. And that results in a 10,000 hour or so lifetime requirement for station keeping for the thruster. What we're talking about is a thruster that can last 40 or 50,000 hours of operation, so multiple years of operation.
But the thrust is tiny on these types of craft, about the equivalent of the weight of a coin resting on a table. But a major benefit is how long they can burn. Instead of the quick and powerful burn for a few minutes like a chemical rocket, these ion thrusters can burn for thousands of hours, which allows that tiny amount of thrust to build up into speeds needed for deep space missions. But solar electric propulsion can also be used closer to Earth as well. Researchers believe that solar electric propulsion can be used as a type of space tug that can take satellites launched at low altitudes and bring them to higher altitudes, potentially saving millions of dollars in propellant costs. Many believe that solar electric propulsion may also be a viable way to service satellites and remove dead satellites as well.
Satellites are a big industry right now, and when they decay and they're no longer of service, it's you can't just
very large spacecraft, asteroids around. We're talking about trying to do a couple things. Provide main propulsion for CubeSats, the very small satellites that are now going into use for university research. Other government agencies are using them for various purposes. And to date, they've been launched without propulsion. So we're creating thrusters that actually use very little power and can be used to both provide prime power for those spacecraft, but also attitude control so that you can reposition and point the satellite the way you want to when you have a sensor looking at Earth. These sensors are also so precise they can be used to point telescopes like the Hubble or the James Webb in the future. And by using these types of thrusters instead of our normal way of positioning these systems, we're hoping to greatly reduce the mass of those satellites. Our hope is that in the end, these systems are very, very scalable. I always use the analogy of the plasma screen TV. Rather than having one sugar cube with a very minute amount of thrust in it, I can string an entire flat panel together with many, many sugar cubes and reach a thrust potential close to the types of systems we're building for that asteroid retrieval mission. Now that's many years in the future, but that's what we're hoping we can get out of that technology because of the efficiency in the basic design.
So far, we've seen really innovative designs for spacecraft solar arrays and thrusters. Another component that needs to be addressed for space missions is battery life and advanced fuel cell technology. Here at NASA Glenn, teams of researchers are working on next-generation batteries and fuel cells for the Advanced Space Power Systems project. The hope is that the work they are doing will revolutionize the types of batteries and fuel cells that are currently being used for space missions.
What we're doing is developing advanced technologies for power systems that will enable future missions, space missions for NASA. Power is obviously a very important aspect for any NASA mission. So it's critically important that for deep space exploration, for instance, where we have very long-term missions, that we have very reliable systems, lightweight, low maintenance systems. So we're currently focusing on developing advanced fuel cell technology and advanced batteries. Batteries are useful for relatively low power, short duration needs, for instance, for extravehicular activity, EVA activities. And fuel cells are of value for higher power, longer duration needs, exceeding 1 kilowatt. Examples would be for rovers that may go out on extended missions, as well as surface systems that would provide power to habitats and tools that the astronauts would need in executing their mission, as well as landers to provide power after landing of the system, scavenging propellants, hydrogen and oxygen from the tanks and producing power for the surface operations.
Without getting too technical, a fuel cell is an electrochemical energy conversion device. It converts the chemicals, hydrogen and oxygen, into water, and in the process it produces electricity. In space applications, it could power any number of devices, including rovers. Because there is a need for lighter and more efficient fuel cells, the team has completely reworked older model fuel cells and produced much more efficient systems. The other electrochemical device that we are all familiar with is the battery. A major difference between a battery and a fuel cell is that a battery has all of its chemicals stored inside, and it converts those chemicals into electricity. The downside is that a battery eventually goes dead, and you either throw it away or recharge it. With a fuel cell, chemicals constantly flow into the cell. It never goes dead. As long as there is a flow of chemicals into the cell, the electricity flows out of the cell. Most fuel cells in use today use hydrogen and oxygen as the chemicals. Because batteries are so important in spaceflight, especially for EVAs or spacewalks, there is a need to dramatically increase the length that the batteries will last. Much of the work in this lab will do just that.
What our main goal is to make batteries better, make them lighter, make them safer, but provide more energy with them as well. So a lot of what we do here focuses on low-level research. What goes into the battery, not the battery itself, the different materials that go into them. And there are main components that go into a battery cell. There's an anode, a cathode, each of them made of a different material. there's a separator, and there's an electrolyte. So we do a little bit of work dabbling in each of those materials to improve how they function and then how they function together.
This work has paid off. These new batteries will soon be going on for further tests into next-gen spacesuits for final validation. And because NASA is owned by the American public, much of the technology being developed today for spaceflight may soon be showing up in devices back here on Earth. As you can see, power and propulsion will be cornerstone elements to future NASA missions. And with each passing day, the brilliant researchers of NASA continue to increase our knowledge and understanding of our universe, moving us into the unknown of deep space, while enhancing all of our lives back here on Earth as well.
We are surrounded by sound every day. From household sounds like dogs barking and people talking, to noise pollution from highways, industry, and planes, our days have gotten very noisy. NASA is working to reduce some of these unwanted noises. As a leader in aeronautics research, NASA is working to reduce the sounds produced by aircraft. The Low Boom Flight Demonstration, a NASA aeronautics mission, includes the design, building, and testing of the X-59 Quiet Supersonic Technology Aircraft, or X-59 Quest for short. The X-59 will be able to fly at supersonic speeds, faster than the speed of sound, without producing a loud sonic boom. But what is a sonic boom? A sonic boom is the thunder-like noise a person on the ground hears when an aircraft or other type of aerospace vehicle flies overhead faster than the speed of sound or supersonic. Picture an aircraft flying through the air. As the aircraft moves, it pushes air out of its way, continuously creating sound waves. These sound waves, or air pressure waves, move away from the aircraft in all directions at the speed of sound, like ripples that form by dropping a pebble in a pond. By increasing the aircraft speed to supersonic, or faster than the speed of sound, the air pressure waves begin to pile up ahead of the airplane and compress, forming shock waves. These are similar to waves that pile up in front of a boat as it moves through water. In the air, the shock waves will move out and away from the aircraft. This creates a sudden change in pressure. The change happens so quickly that when the energy from the shock wave reaches our ears, it's heard as a loud crack of a sonic boom. So how is NASA trying to quiet the sonic boom with the X-59? Let's find out from an X-59 NASA engineer.
Well, the X-59 is designed to generate a quiet sonic boom when it flies supersonically. Traditional airplanes that fly supersonically, such as the Concorde or military jets, develop a very loud sonic boom as they fly over the ground. It's very disturbing to people on the ground, and that's a big impediment to being able to just fly commercially all the time supersonically. So this airplane is a demonstration of a capability that we think we developed to be able to shape the airplane such that it will not generate that loud sonic boom. And so if you look at a picture of the airplane design, you'll see that unlike a normal airplane, it's very long and slender. And the reason for that is to be able to shape the volume distribution and the lift distribution over the airplane in such a way that the shocks don't all coalesce into a very strong front and rear shocks that make that loud sonic boom. The airplane is designed to fly at a high altitude for a number of reasons, one of which is the distance away from the ground reduces the noise from the sonic booms. So higher, farther away, it would be quieter. The other is, of course, that the airplane is designed such that the lift distribution over the airplane is what we need at a given angle of attack. And the angle of attack is the wind angle going into the airplane, how it touches the airplane. And so to get that angle correctly at the Mach number we want to fly at, puts you up at 55,000 feet, mid-50s. So the biggest challenge historically has been just in the capability of being able to analyze how the airplane is going to act. We've recently developed the tools to be able to predict how the sonic boom will be produced on the airplane and to be able to trace that to features on the airplane. And then that allows us to design the airplane like you see in the picture, the long, slender airplane that then develops the quiet sonic boom.
Thank you for watching, and don't forget to watch our next video about NASA's long history with supersonic flight.
Amanda Gurdy-Jensen, and I'm the Senior Production Manager for Final Assembly for NASA's Space Launch System rocket, and this is Rocket Science in 60 seconds. The core stage is the spine of the SLS rocket. Its 2 huge propellant tanks and 4 RS-25 engines provide over 2 million pounds of thrust to launch NASA's Artemis missions to the moon. Because of the size of the hardware, the core stage components are connected in 3 major joins. First, we mate the forward skirt to the liquid oxygen tank to the inner tank to form the top part of the rocket, or the forward join. Then horizontally, we mate the liquid hydrogen tank, followed finally by the engine section. To properly align the flanges as they come together, we use live photogrammetry on 6 bolt locations.
Measured 260 feet wide and 195 feet deep when it was observed. Throughout the mission, IceBridge was able to map rifts in ice shelves prior to major calving events. And while these events are part of a natural cycle, IceBridge's observations helped scientists better record the changes in calving frequency and model how they may be related to a thinning ice shelf. The motion of the Antarctic ice sheet, the largest ice sheet in the world, is heavily influenced by the topography of the bedrock underneath. In 2013, The British Antarctic Survey used over 25 million measurements collected by IceBridge and other projects to develop a 3D map of Antarctica's bedrock topography. Called BedMap 2, it provided unprecedented detail of how the continent's bedrock shaped the flow of the ice sheet. Data collected by IceBridge enabled many discoveries in the Arctic as well. A team from the University of Bristol used IceBridge's radar data along with other data sets to uncover a 400-mile-long canyon buried under nearly 2 miles of ice. This hidden canyon is longer than any other known on Earth and provides a critical clue to modeling how melting ice is funneled into the Arctic Ocean. Using ice-penetrating radar data collected by IceBridge, scientists were able to build the first ever age map of the layers deep inside the Greenland ice sheet. For the first time, scientists can navigate the history of Greenland's ice layers, extending previously collected ice cores to better understand the ice sheet's history and help build models of its future. An international team of scientists used decades of NASA data to uncover a massive impact crater hiding beneath the Hiawatha Glacier in northwest Greenland. At roughly 1,000 feet deep and more than 19 miles wide, it is potentially one of the youngest large impact craters on Earth.
6, that's gonna 5, 4, 3, 2, 1. Mark on the overpass, 0435, 350.
Ice was bridged on April 8, 2019, with the direct underflight of the ISAT-2 satellite over Arctic sea ice. For the first time, both ISAT-2 and IceBridge would be taking the same elevation measurements over the same ice. These mirrored measurements were critical in validating the satellite's instruments and continue the legacy of IceBridge after the mission was completed. Over the course of its 11-year mission, IceBridge completed 1,056 scientific flights and provided a wellspring of data that fueled the publication of more than 660 papers and counting. The mission provided new insight into the processes driving the changes in the cryosphere, helping scientists better understand what we can expect in the future.
Early in its history, Mars had a far more hospitable climate than the one that we see today, with a thick atmosphere and abundant flowing water. So how did it evolve from warm and wet to cold and dry? Since 2015, NASA's MAVEN mission has been investigating this question by studying the red planet's upper atmosphere. Now, it has mapped high-altitude global wind patterns at Mars for the first time. During the closest part of its orbit, MAVEN skims through the upper atmosphere, ingesting air molecules and determining their composition with an instrument called NGEMS. MAVEN can also rotate NGEMS back and forth to measure the air's velocity. These measurements provide a snapshot of wind speed and direction along a track of MAVEN's orbit. Because the orbit evolves over time, or precesses, the spacecraft's closest approach to Mars drifts across the planet, allowing it to take snapshots at different locations. Over the past 4 years, MAVEN's tracks have added up, crisscrossing Mars at many locations and at various seasons and times of day, wrapping the planet in a web of observations. The measurements reveal how the winds vary with location and evolve throughout the Martian year. Now, scientists have used MAVEN data to build a global map of wind currents roughly 200 kilometers above Mars, the first time that winds have been mapped globally and at such high altitude anywhere beyond Earth. Within the new map, scientists discovered an unexpected feature: imprints of rugged terrain far below. As an example, during 2 of its orbits, MAVEN saw winds above the Tharsis Plateau diverting away from elevated terrain, driven by giant shield volcanoes reaching twice the height of Mount Everest. Here's how the process works. Down at the Martian surface, winds are forced around and over obstacles when they encounter mountainous terrain. Disturbances in surface-level winds also disturb the air above, propagating up through the atmosphere as gravity waves. When they reach the upper atmosphere, the gravity waves block the high-altitude winds, causing them to alter course, and allowing MAVEN to sense the presence of mountains and valleys on the surface while skimming the edge of space. High above Mars, MAVEN is studying the upper atmosphere and reaching out to feel the breeze. It has now made the first measurement of high-altitude global circulation patterns and discovered a surprising connection to features on the surface. These measurements also shed new light on ancient Mars with its thick atmosphere and its warm, wet climate. By revealing how the climate of Mars works today, MAVEN is helping scientists piece together the early chapters of its dramatic history.
Okay, folks. Happy holidays.
Thanks. Happy holidays. Come on, sweetie.
Look at my rocket, Mommy. I'm gonna be the first woman on the moon.
Yes, and maybe even Mars. Watch the snow.
Okay, guys. It's all clear.
Hi, I'm Mark Weiss, and I'm the Logistics Element Manager for NASA's Gateway program. And this is Ask NASA. We're here to answer your questions about Gateway. All right, let's get to the questions. First one we've got in the mailbag. Why can't we just land on the moon? We can. We did that already. Gateway is not about just landing on the moon. Gateway is about giving us access to the entire moon and doing it in a reusable, sustainable manner. Gateway is our command and service module that will enable us to explore the moon. It's a small spaceship, and it enables us to dock Orion, get down to the surface of the moon, and practice at a place that's really close, so we can eventually explore beyond to Mars. All right, next question. When will the first module be ready? So Gateway's first module is the power propulsion element, right now scheduled to launch by the end of calendar year 2022. That's what allows us to have all the power to start to assemble Gateway and be ready for a 2024 Boots on the Moon. Will the Gateway have cameras so people can watch live action? Scientists love pictures. But so do you, right? We want to share this with the American people. In this world of hashtag what's going on with Gateway, we want to share that with everybody. We will definitely be sharing what we're doing to go down to the surface of the moon and living aboard Gateway.
What's your favorite sci-fi character?
Darth Vader?
If the moon was made of cheese, could you smell it from Gateway?
No, because the smell won't travel in space.
How far is Gateway from Earth?
It's far. Gateway's in deep space. So we all can see space station fly above Earth. It's a couple hours drive equivalent above us, and when the sun reflects, those solar arrays are huge. Gateway's nowhere near that size, and it's 250,000 miles away at the moon, so it's going to be much harder for us to spot it out there.
Are we taking science research to Gateway like we do with Space Station?
Absolutely. So we want to definitely take advantage of that environment out by the moon where there's less interference of what's going on here at Earth so we can study the planets beyond.
What's your favorite part of your job?
The people. Always the people. We work with amazing people. NASA's an amazing place to work.
How many astronauts does it take to change a light bulb on Gateway?
None. They don't live up there all the time like they do on space stations, so we have to develop the right inter-vehicle robotics to make sure we can do this without them even being there. How will air and water be supplied? So water's not coming in bottles like this. That's the challenge we have, to set up a commercial supply chain to deep space. We don't have a rocket launching every single day, so we have to figure this out and make sure we have everything our crew needs: supplies, science equipment, and all of the equipment they need to go down to the surface of the moon. And the air they need to breathe. Where's my eggnog? Did someone take my eggnog? It's got EVA mittens.
Do you have a question for NASA? Send your questions to our experts using hashtag AskNASA.
It's one small step for man, one giant leap for mankind.
Jim, so great to see you. I can't believe I'm at Johnson Space Center.
Thank you for being here. Welcome to the Blue Control Room here at the Johnson Space Center in Houston, Texas.
I love all the patches on the wall. What does this mean?
So these are all different missions of the past that NASA has been involved in. And what we are doing now is we are building upon those successes to go back to the moon sustainably. We know that there's hundreds of millions of tons of water ice on the south pole of the moon. Water ice represents life support.
No way. How is this different than 50 years ago?
50 years ago, we went under the name Apollo. And this time we're going under the name of Apollo's twin sister, Artemis. We go with a very diverse, highly qualified astronaut corps that includes women. We learn how to live and work on another world, and ultimately we take all of that knowledge to Mars.
So we're actually going to stay on the moon?
Absolutely. Unlike last time, this time we're going to stay.
But how are we going to get there?
We are in the Orion crew capsule, which is the vehicle that's going to take our astronauts to the moon. This crew capsule is going to go to a space station called Gateway. Gateway will be in orbit around the moon for 15 years.
You got to watch your head in these things. What does it feel like to walk on the moon?
When we go to the moon, we're going to have 1/6 the gravity of the Earth. And what? Oh, there you are. You look at you. You're already in 1/6 the gravity of the Earth.
How are NASA's investments in space exploration having positive impact for everyday Americans?
Right now, on the International Space Station, we are proving that we can compound pharmaceuticals in a way that cannot be done on Earth. We can print in 3 dimensions human organs using adult stem cells. Space is transforming human lives right here on Earth.
How important is having life-size mock-ups for astronaut training?
Well, it's absolutely critical. In order for the astronauts to be ready to do what needs to be done on every mission, they have to train. So what we have to do is be able to replicate the harsh environment of space and demonstrate neutral buoyancy and or weightlessness. And we use the Neutral Buoyancy Lab in order to replicate those effects.
Whoa, this place is big. What am I looking at in there?
Inside this pool, we have a replica of the International Space Station. Our astronauts actually get to practice doing spacewalks underwater. Newton's laws of physics apply here. So if you're in space and you try to turn a wrench, you might turn the wrench, but you also might turn yourself. And our astronauts get training to learn how to deal with those effects.
Jim, I think I have what it takes, but I have to ask, what characteristics do you look for?
When we do things, the entire world sees it. What we are looking for at NASA are people who want to make history. And as long as we keep doing absolutely stunning achievements, we will always attract the absolute best.
You are the definition of humans and technology coming together to change the world. What excites you going forward for NASA?
We are writing brand new chapters in history books and science books. It's navigation. We think about GPS, communications, the way we produce food, the way we produce energy, the way we predict weather, how we understand climate. All of these things are capabilities and technologies born from this little agency called NASA that has the best brand America has to offer.
Jim, seeing everything firsthand has left me stunned, but as a kid, I've always wanted to put on the suit. Can I do that?
Today is your lucky day. Absolutely, I'd love to have you try on a spacesuit. Every spacesuit is a spaceship designed specifically for the astronaut that wears it. We're talking about thermal environments of minus 200 degrees and plus 200 degrees, and we're talking about the vacuum of deep space.
Jim, sign me up. I'm ready to go. Thanks again for showing me around today.
It's been my honor, and we will indeed sign you up.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there was no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach, pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
Hello, I'm NASA Associate Administrator for Science, Thomas Zurbuchen. NASA is going to the moon with the Artemis program, and American companies of all sizes want to help our nation make its next giant leap. It is my pleasure to announce the companies who are joining the pool of NASA industry partners who will help our nation enable the first woman and next man to reach the lunar surface by 2024 and conduct significant science investigations. Through NASA's commercial lunar payload services, we're sending science and technology demonstrations to the lunar surface beginning in 2021. These payloads will help us study the moon and prove technologies that will need to eventually travel to Mars. Today, 5 new companies joined this great initiative. I want to congratulate the new CLIPS participants: Blue Origin, Ceres Robotics, Sierra Nevada Corporation, SpaceX, and Tyvak Nano Satellite Systems. We look forward